Hello all, and here are our 2.3 notes for using reasoning to find a counterexample to a conjecture. So we've already talked about what conjectures are. We mentioned counterexamples yesterday. So when we're using inductive reasoning, to show that a conjecture is true, you have to show that it's true for all cases. So like we said before, it's hard to do if we're dealing with numbers because numbers are infinite. They go on forever. It's impossible to show that it's true for all cases. So there's no way to prove a conjecture using inductive reasoning because all it takes is one counterexample to show that it is not true. So you can show a conjecture is false by finding just one counterexample. So what a counterexample is. So a counterexample is basically an example that counters your conjecture. So it is a specific case for which a conjecture is false. So a specific case for which a conjecture is false. Okay, so it makes it untrue or invalidates it. So we're going to be looking at a couple of examples and finding counterexamples for them. So our first example, we're going to examine this pattern in the product of 11 and another two-digit number. So specifically two-digit numbers and the product of 11. So we're not going to be checking any smaller numbers or larger numbers than 2 digits. This is what we're going to be checking. This is a pattern we're going to be looking at. So we're going to make a conjecture about this pattern. So I did not give you these examples, so you will have to write down part of it. Okay, so pause the video right now, see if you can figure out how we can get from this two-digit number to what the product is. So see if you can find any patterns in the digits before I go and ruin it for you. So the first thing that I'm looking at is the first digit here and the first digit in our product. So 1 and 1, 1 and 1, 2 and 2, 4 and 4. So it seems like the first digit is the same in both my two-digit number and in my product. The next thing I notice is the second digit. So 1, 2, 6, and 3. I also end in a 1, 2, 6, and 3. Then the very last thing is how do I get this 2, 3, 8, and 7 based on these two digits? So you might notice that you can get that 2, 3, 8, and 7 by adding, oh goodness gracious. There we go. Adding our first and second digits. So 1 plus 1, I get 2. 1 plus 2, I get 3. 2 plus 6, I get 8. 4 plus 3, I get 7. Okay, so my conjecture is, all right, how do I get from this two-digit number to my product? How I get there is I can take the first digit of my two-digit number, and that's the first digit of my product. Okay, so the product of 11 and two-digit number will have our first digit in our product be the same as the first digit in our number, and same with the last digit. So the last digit of our two-digit number will be the last digit of our product. And that middle number is the sum of my two digits and my two-digit number. So this is kind of confusing and wordy. Sometimes it is nicer to just show it kind of algebraically or mathematically. So how I can do that, if I relegate these two digits to being, say, A and B, then I know my product will be A on this outside, B on this outside, and in the middle, I take A plus B. Now just unsquishing that. So here's my two-digit number multiplied by 11. Oops. I will get A, then A plus B, and then B. So on the outside, add them up to get the number on the inside. Okay, so there we go. Either way of writing our conjecture, either in words or kind of algebraically, is fine. For question B, we want to find a counterexample. So we want to find an example where this rule will not work. So I would pause the video, see if you can find a counterexample first before I go into just finding one for me. Right. So taking a look, we can start with just some 2-digit numbers. So I can try, say, like 22. So just trying some examples. So 22 times 11. So if I do my trick, so it'll have 2 and a 2, and then a 2 plus 2 is 4. 22 times 11 is 242. Yeah, that's right. 18 times 11, just pick another one. 18 times 11 would be like 1, and then an 8, and an 8 plus 1, I'd get a 9. And that works out as well. 18 times 11 is 198. But that would actually get me thinking, like, what happens? So I got to 9. What happens if I got to 10? Like, what happens if my 2 digits add up to more than 10? Well, my rules still work, okay? Because I'm going to have some carryover there. So let's try it. So let's pick like 5 and 5, 55. Let's do 55 times 11. So that'll give us 10. So 5 plus 5 is 10. So when I take a look here, 55 times 11 should be 605. So I see that my rule did not work. Okay, so this by itself is enough to prove that my conjecture is incorrect. So this is my counterexample. It doesn't work. Okay, I could find more, but all I really need is one. There are more, of course, that I could find. I could do like 70, let's say 74 times 11. So using my trick, it should be a 7 and a 4, and then 7 plus 4 is 11. And it should be 814. Okay, so I can find more counterexamples. But we were just required to find one, but there is more. So now we need to revise our conjecture. So it's not that it didn't work out for all numbers, or it does work for some numbers, but not others. So if I was going to revise this, I would have to say that my first, like my 2-digit number, the digits can't add up to more than 10. So provided the sum of the digits in the 2-digit number is less than 10, or algebraically, since I was using A and B above there, I can say that A plus B has to be smaller than 10. And now this isn't necessary. I've done my crawlery, I've revised it, but I could actually find another pattern here. So if I look at the last 2 digits, the last 2 digits are fine. It's just this first digit, like these first digits actually. So it's 5 in this one, and then this 7 in this one. So the last 2 were okay. Now if I take a look at that 5 and that 1, I can see that I can get a 6, and that 7 and that 1. If I add those together, I can get an 8. So I could go one step further with my revision of my conjecture and say, based on the 2 examples that I've done so far, the 2 counterexamples that I found, that if I do add that carryover 1 to the first digit, I can get the correct product. So yeah, if it is, add the carryover 1 from the sum to the first digit of the product. And we could check that with some more examples to see if that works out all the time, or find another counterexample to see if that doesn't work. But that's the most that we really have to do for this question. And you didn't even have to go this far. So we're going to prove or disprove the following conjecture for example 2. So the difference between consecutive perfect squares is always a prime number. So how we're going to check this is we're going to start checking our consecutive squares. So consecutive means like one after the other, one in a row. So consecutive integers would be like 1, 2, 3, or 7, 8, 9, 42, 43, 44. Consecutive perfect squares will be like, okay, well, I'm starting with 1. then I'm going to 1 squared is 1. 2 squared would be 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And we're going to start checking, seeing if the difference between them, so difference is subtraction, is going to always be a prime number. So taking a look here. So the difference between 1 and 4 is, 4 minus 1, and that's 3. Okay, 3 is a prime number working so far. 4 and 9 is 5. 9 and 16, we're getting 7. So far working out, also prime. 16 and 25, I get 9. Okay, so as soon as I get to here, I have my counterexample. So 9 is not a prime number. And we could even find more. So we could find more counterexamples. It's not necessary, but we could go to our next, perfect square. So 36 or 49 and 64. So we could see if there are more of them, or maybe it's just that one time. So 25 to 36, I get 11. So it works out, here's 13. 49 to 64, I get 15. Okay, so here's another one. So 15 is also not a prime number. Okay, so I already found one counterexample. I don't need to find more, but I do have more than one counterexample that you could use. It's not just as soon as you get to the first one. It doesn't matter which counterexample you use, so long as it is a counterexample. Only takes one. So this conjecture is incorrect because either 9 or 15 are not prime numbers. They are composite numbers because they are composed of more than one factor. Okay, so 9 could be 3 and 3, 15 could be 3 and 5. They are not prime numbers. Now, if you feel like you're good to go, you get it, you do not have to do example 3 here. I won't be looking for it in your notes or anything. You can just start. If you want to do another one together to see if you can find a counterexample, go through this one with me. If not, just go to the end of this video to see what your assignment is going to be for this section. Okay, so if you're following along, thanks for staying. Let's take a look at what this pattern is. So I can see that I'm multiplying a number to 8, adding a number to it and getting a result. Okay, so I can see that this is going up by 1 every time. Okay, and then over here, I'm kind of getting almost, If you want to do another example together, stay here with me and we'll do this one. Otherwise, if you feel like you've gotten the hang of it, you're good, you don't want to do another one together, you can just skip this example, go to the end of the notes of the video here and take a look at your assignment and get going. All right, so if you're staying, take a pause here and see if you can find the pattern before I start going through it. Okay. So in each subsequent line, I'm adding something. So I'm adding something every time. So first I have 1 times 8 plus 1 equals 9. So the 8 seems to stay the same. I'm always multiplying a number by 8. But as I go down, the numbers are changing. So I always have a 9, starts with a 9. Okay, then I'm adding an 8 as I go to the next one, then 7, then 6. So we can guess that based on this pattern that I'm seeing over on the right side, I would have a 9 on my next one, an 8, a 7, a 6, and then probably a 5, right? Okay, and then this number here that I'm adding onto this product is increasing by 1 every time. So I assume that this will be 5. Okay, I'm multiplying by 8. And this number next will be 1, 2, 3, 4, and then 5. So in our calculators, we can check, is 12,345 times 8 plus 5, 98,765. And sure enough, it is. Okay, so this one also works out. So what I'd like you to do now is pause again, now that we've established the pattern, and see where you'll find the counterexample or a counterexample. You might already be able to think of what one is. So pause and then unpause when you found one. So maybe you got to where I did. Maybe you checked all of these numbers using a calculator that has enough digits that you can actually check, and got to here. Or maybe you realize that because of our earlier example, or just logic, that what happens when we start getting double-digit numbers. So maybe it works for 5, 6, 7, 8, 9. But what happens when I get to 10? Because as soon as I get to 10, I'm adding 2 digits on instead of just 1 digit. And what will I be getting as an answer then? Like, how is this pattern going to continue? Okay, so maybe you get all the way up to there. Maybe you're just like, well, what's going to happen at 10? So skipping all of those steps, or like checking every single one. So his conjecture is not true. However, we can revise it to make it true. So we could add the following to when you're adding, like when the add end right here is less than 10, or when it is a 1-digit number, as long as your adding number here that tells you what your other things are going to be, it is a 1-digit number. We can make a corollary, but here we just have a counterexample right there. So your assignment is page 23, 3 to 5, 8, 9, 14, and 17 as an extension if you finish early or want some extra brain exercise or just want to know you're doing good. Also, you can also complete 13 and 16, but you do not have to. That is optional. A couple hints. Don't forget that like negative numbers and fractions and decimals are numbers too. Don't count them out. And the set of natural numbers is like your counting numbers, so like 1, 2, 3, 4, 5, 6, just your counting numbers. So it doesn't go into negatives, doesn't have halves, doesn't have like any decimal points, just your natural counting numbers. So not even 0, just going on like that. So our natural numbers are like 1, 2, 3, 4, so on and so forth. Okay, with that, you should be good to go. Bye.